I think that's the case. Okay. So, work and power. So we've been talking about energy this whole year. Work and power is specifically how energy moves between various places or various types. So, yeah. Anyway, I'll like to read that later if you want. It's a fun quote from Dave Barry. From Dave Barry. Okay, so, yeah. Total mechanical energy. So far we've learned about two types of energy. We've learned about potential energy and kinetic energy. When put together, they are total mechanical energy. Total mechanical energy is usually given the letter U. I guess because they didn't want to say TME. But total mechanical energy is the sum of the kinetic energy and potential energy. So, objects that fall, they lose potential energy and gain kinetic energy. So that's total mechanical energy. So far we talked about kinetic and potential. Once again, kinetic energy is the energy of movement, 1/2 mv squared. Anything that's moving has kinetic energy. And we talked about last week why it is that you have to allow yourself 4 times the distance when you travel twice as fast. And that's because if you're traveling twice as fast, your kinetic energy will be 4 times as large. And to arrest your kinetic energy, you have to do work, which is work is force times distance. Okay, so just like we talked about yesterday, kind of off the cuff, really, why is it you have to travel 4 times further when you have twice the speed? Because v is squared. If v gets doubled, that's double squared, which is 4 times the kinetic energy. And to arrest all of your kinetic energy, your brakes have to do 4 times as much work to arrest 4 times as much kinetic energy. So work is force times distance, which is what your brakes do. They apply a force over a distance. Potential energy is energy of storage or energy of state. And the potential energy we've talked about so far is gravitational potential energy, which is how much energy this ball has if I drop it on a spider. Squish. It will do the work on a spider. The higher I drop it, the more it squishes the spider. So that is just one of a lot of potential energies. We're going to learn about elastic potential energy here in a few minutes, or at the end of class, or tomorrow. And then we'll also learn about some other energies from heat and from fluids and from magnetism throughout the year. Okay, Gesundheit. So how are we doing so far? Question?
What is work measured?
Joules. That's the great thing. Everything is measured in joules. Work is the change in energy, also measured in joules. All energy is measured in joules. And if you saw that little drawing on the title slide, that was a drawing of James Prescott Joule with one of his machines. He did something pretty cool. These are thermometers and paddle wheels, but the Joule experiment was super, super simple. What he did is he had a big bucket of water, and he put in that bucket a paddle wheel, basically a stick with paddles on it. So when the paddle wheel turned, the water got churned up. And then, just like you had weights over pulleys that pulled the carts, he had a weight over a pulley, only it spun the paddle wheel. And when the weights fell, the paddle wheel spun. And guess what happened to the water? It got hotter. Yeah, kind of fun. So if you want to experience the same process with far less efficiency, get yourself a bag of, actually a bottle of popcorn that you pop in an air popper, and just kind of shake it, and just shake it, shake it, shake it, keep shaking, keep shaking, keep shaking, and eventually you put your hand in it, it'll be warm from all the friction and all the banging and all the movement. So that's kind of fun. Okay, questions before we move on? So, again, we've discussed kinetic energy, we've discussed potential energy. We alluded to force last week, and I talked about what work is. Work is a change in energy. Oh, were you not done? You were done? Okay, now here's the thing about work. Work must be done in the same direction as force. And why is that? Why is work only done when, force must be done in the same direction as distance, displacement, in order for work to be done.
Wait, what?
In order for work to be done, force and displacement have to be in the same direction. Why is that?
Does it have to do with static?
thanks for volunteering something. Any other volunteers?
Otherwise, it would just counteract each other, and so there wouldn't be anything getting done.
Does that give you a hint, Justin?
If one went the opposite direction, would work be negative?
Yes. Yeah. If force was in the opposite direction of distance, then work would be negative. But what does that mean? When you see that over something, what does that mean?
It's a vector.
It's a vector. And remember, we learned in projectiles that vectors at right angles don't interact with each other. So if you have a force that's at a right angle to displacement, no work can be done because vectors at right angles don't interact. Does that make sense? So you have to have some sort of component of force in the direction of displacement to get any kind of work. So with that idea, if you have a situation where you are carrying a box across the room, I'm carrying the football across the room. If I'm carrying the football across the room, am I doing work on the football? No. Friction, however, is, if I'm applying an upward force on the ball and the ball is moving horizontally, that is no work. However, friction, what direction is friction acting when I'm moving it? That. And it's moving this way, so friction is basically doing work on the ball, but no, I'm not doing anything. Now if I lift the ball up, am I doing work on it? Yeah, because I'm increasing its potential energy. And when gravity allows it to fall, is gravity doing work on the ball? Yeah, because gravity's pulling down with its weight, weight times distance, that's also work. So, in this situation, is the guy doing any work? No, because he's applying an upward force and the direction of motion is horizontal. What if you're mowing a lawn with one of those old mowers that has the spinning blades? Are you doing work? Yeah, because there is a component. If you're applying a force that way, there is a component in the horizontal direction, Fx. So there is distance that way, force that way. So some work is being done. When you hit a golf ball, are you doing work on it? Yeah, because you're going to apply a force hopefully in that direction. It's also going to move in that direction. You're going to apply a force that way, distance that way. When you lift a barbell over your head, are you doing work on it?
Yeah.
Yeah. When you hold it there, are you doing work on it? No. So if it has displacement as you lift it, then you're doing work. But when displacement is 0, no more work. Does this idea make sense? What we're talking about?
It's developing.
Okay. And then this is a video. If we have time, I will show you. It's a really cool video on does this work? See, Mythbusters doesn't always get it right because. As I know, right? There haven't been Mythbusters for like 5 years, but when they were going on, not everything they did was right because there was a lot of things that kind of crept in that they didn't realize, and so there were bits of friction or angles that they could not control. The issue that I have with Mythbusters, I love Mythbusters, they're great. The issue that I have with Mythbusters is they had a one and done mentality. It's like they did it one time and they called it good. They never repeated it, or they never accounted for certain variables. Like, what if we did this? Would this affect it? They just did it once and called it good. Which is honestly, if you're blowing up a cement truck, one and done is all you get. But that's not good science. So good science is repeatable. And I want to show you a YouTube because I simply don't have the mechanical skill to build what the guy built. I want to show you a YouTube that demonstrates this really well. But that is for another day. Don't let me forget. By the end of the unit, I want to talk about that. Okay. So, shall we move on? Let's move on. Okay. Energy is never created or destroyed. It's only transferred between species or converted into different forms. Friction tends to turn energy into heat. So most of the time when we lose energy, we lose it to heat. And that's just one of the things that's almost impossible to take care of outside of a computer simulation. So it's just, So energy, the conservation of energy is pretty important. It never gets created or destroyed. It just gets moved around. Unlike entropy, which is constantly being created, energy does not get created or destroyed. So this animation is an animation of a skier at the top of a hill, and we're going to assume that the hill is perfectly slick with a 0 friction coefficient, so it's perfectly slick, until we get to the unpacked snow. When the unpacked snow kicks in, there's friction slowing him down. So at the top of the hill, he has a whole bunch of what? Potential energy. And 0 what? Kinetic energy. And as he falls to the bottom, he loses his potential and it becomes kinetic. But then something interesting happens when he hits the friction. Now friction is doing a bunch of work on the snow, or sorry, the snow is doing a bunch of friction work on the sled, slowing it down. So he loses his kinetic energy. So he starts with potential. As he slides down the hill, he loses potential, gains kinetic, and then once he gets to the bottom, he's got all kinetic, and then he starts hitting the friction snow. The snow does friction, and his kinetic is reduced, and his work is reduced. Notice what happens to his total mechanical energy as he's converting his potential into his kinetic. What happens to his total mechanical energy?
Stays the same.
Yeah, it stays the same. So his total mechanical energy is simply the sum, once again, the sum of kinetic and potential. So his total mechanical energy does not change until friction kicks in. Then friction starts sucking that speed away. And you can actually do the math and do this, okay, he's 52 meters up, he's going to start at that speed. And hopefully if we did the math, then we could look at it and say, oh, so the change in PE, the delta of the PE, is going to become the delta of the KE, which means the mg delta H is going to equal 1/2 m delta V squared. So hopefully at any point in time or any height, you can say these things work out pretty well. Also fun, we talked about this on Thursday, also fun when, or Wednesday, it was Wednesday, we talked about it on Wednesday, since the masses are on both sides, if you're talking about the same piece of equipment, then G delta H just equals 1/2 delta V squared, because m's can cancel out. Can you see how m's cancel out?
Yeah.
And that becomes that? Okay. All right. So I got this thing last year. It's several tracks. Here's my several tracks. Whew. So and then another one that is ideally as high as, well, as it could be. This thing does take into account friction, so they actually made this pretty decent. And all the paths are different. So this first path, okay, and then this bottom path has a lesser straight path, and then this path is just a straight down path the whole time. Zoom. And then this path goes down really fast, and then it plateaus out and slowed down here. So this one is less steep than really steep. This one is less steep and then even steeper for a shorter distance. This one is less steep the entire time. And this one is really steep and then less steep. So
They're kind of like
using these three, I'm going to show you how this one goes. This one goes like this. Okay? And this one goes like this. And this one goes like this. And this one goes like this. So these three paths, or sorry, these four paths, if you can see it, predict with your neighbor which one of the balls will get to the end first. So we got one that's less steep than really steep, one that's less steep than less steep, one that's equally steep the whole time, and one that's really steep than less steep. So with your neighbor, take a minute and predict which of the three is going to reach the bottom first. I'm sorry? Like I said, which of the four is going to get to the bottom
You
first?
really want to eliminate one of the paths.
Apparently I do.
Want to tell us which one it is that we're eliminating?
No, I don't.
No. We don't get to know.
It must be on Monday.
I thought it was 7.
It's true.
Either equal or they're all the same.
If I can number these. Get a pen and number them.
They're all the same.
Okay, can you see all of them? Oh, you can. Okay.
Yeah.
So make
At one point, you see all four.
1, 2, 3, 4. There we go. Hey, turns out there are 4.
Wow. You just ignore number 2. You just ignore number 2. Ignore all. Hey, answer this one. None of the balls will get to the end.
You better mark it for me too. Okay.
Oh, bro, that's the opposite of
1, 2, 3, and 4. All right, so you've had a minute or two to think about this. They're all going to start at the same height. They're all going to end at the same height. So who believes that 1 is going to be the fastest? Could get to the bottom the fastest? Nobody. Who believes 2 is going to get to the bottom the fastest? Nobody. Who believes 3 is going to get to the bottom the fastest? About 2/3 of you. Who's going to get to think 4 is going to get to the fastest? The remaining handful. Okay. So here we go. For those who think it's going to be what you think it is, why do you think it is going to be what you think it is?
Because the way it is.
Ah, okay, here we'll see.
What was that?
It was 2, 4, 3, 1. 2, 4, 3, 1. So sorry, right, 3, 2, 3, 4, 2, 1. 3, 4,
I was
2,
like,
1.
it was definitely 3 though.
It was definitely 3. So why was 3 the fastest?
Because
Shortest direct.
Shortest distance? That makes sense.
Oh, yeah.
It also speeds up a lot sooner than the other ones.
That's because the fourth one starts flatter.
Yeah. The 4th is basically slow, this part, and then faster, but by the time it already gets there, 3's already been cruising for a long time. And then 1's obviously the slowest because it has to go slow for a long time. So you want to see it again?
Yes. 3 bounce
Spires when they turn the board around, so the curved part is there. They might not just bounce off.
They come like get stuck?
Maybe.
We'll see.
Yay,
science and technology. Here we go again.
I mean, they all went into the sink that time.
That's a good point. All right, so that's fun. Now, I've tried. You're limited in what you get when you buy stuff from wherever they were built in China. But I tried to get these guys lined up. Now, they all start at the same height, and accounting for friction, they should all end at the same height, right? So if there were no friction, they should all end up at the same height. Well, it turns out that friction is actually pretty minimal. That one goes up and over because that one has a lot of friction. So if we ignore the obvious number 3 winner, I'll get it later.
It's back.
It's back in the sink.
They like the sink.
Yeah. There we go. We made it. Let's see if number 1.
He didn't change tracks.
Let's see if number 1 makes it to the same point. They actually they make this thing and they anticipate the friction.
Wait,
So
3's the only one that goes over?
yeah, number 3 is the only one that goes over because it's got a much shorter distance. So since it has a much shorter distance, friction acts on it for a lot less time or a lot less distance. It's under the computer card. Anyway, see, I told you there were 3. So yeah, if you ignore 3,
It was a prophecy.
1, 2, and 4 have pretty much the same overall distance, so friction acts on about the same, so they go about the same height. If there were no friction at all, they would all get up to the same height, and the height they would get to would be right about here, if there were no friction.
That's where like 3 is.
I'm going to forget about that marble and find it like somewhere in June. Okay, so vertical movement. Quite simply, when you throw a ball into the air, you're going to give it a whole bunch of energy, and it's going to have maximum potential when?
Oh
When will it have maximum potential?
At the very
no. Top.
At the very top. It's going to have maximum potential at the very top. When will it have maximum kinetic? Yeah, as at my hand, and also, ideal if I catch it, also when I catch it, right?
How high does that go up? 8 feet.
About that high. No, it goes up another, probably another 8 or 10 feet.
Really?
It goes way up there. Yeah, it's as high as the library is high, so it goes up there.
Why only that portion though?
Timed out
I want
don't
the actual
know.
distance.
Not
Which
even
is 1/8 squared. If it's
Hey, Tom.
I don't think he is.
So when you fire a projectile or launch a projectile or throw a projectile, you have maximum kinetic energy at the bottom of the path, and then as the thing rises, it loses potential energy, loses kinetic energy, gains potential energy, and at the top of the trip we have maximum potential, and as far as the horizontal direction goes, we ignore it. As far as the vertical direction goes, you have maximum potential, minimum kinetic. Roller coaster. What is this?
That's a great sound.
Yeah, you might have noticed the announcements are. Okay, so is that because not even working? Wonderful. Okay, you might have noticed the announcements don't work because they're super quiet. So I have to crank the audio up all the way and it makes my fun computer go buzz. Alright, so this alright, moving on.
Miss Verlick just moved on. She didn't even.
Yeah, she's like, we can't hear it. Let's move on.
Hope there was nothing important.
And that's all I'm going to say about it, because about 4 years ago when they started the video announcements, I said them like that and someone came and yelled at me. You think kids are stupid. No, they just think their teacher doesn't know how to use the equipment. Ooh. I didn't say that.
What?
Yeah, I'm done making friends. So anyway,
I'll be your friend.
thank you.
We'll be your friend.
All right, so take a look at a projectile. So again, when a projectile launches, it goes up and then it comes back down. Now this is a projectile with both X and Y motion. Take a look at the graphs of potential and kinetic energy. Okay. Total mechanical energy is going to be constant until it hits the ground and becomes zero. But take a look at the potential, and by PES they say like chemical energy, but take a look at the graphs of potential and kinetic energy.
They're like opposite of each other, kind of. But no, really, they are.
The sum, their sum is going to be constant. So as kinetic goes up, potential is going to go down. As kinetic goes down, potential is going to go up.
And then they meet in the middle.
Yeah, there is a point where they're equal, but that's not all that important. But in this case, this is what's important here. In this case, what does kinetic energy not do? It doesn't go to zero. Why?
Because it's constantly moving.
Yeah. At the highest point, when it gets launched, it has both Vy and Vx. When it gets to the highest point, what does it still have a whole lot of?
VX.
It still has Vx. Now the Vy is constantly going to get smaller until it's like almost zero, and then zero is Vy, and then you have a little Vy, then more Vy, and then a whole bunch more Vy, but the Vx is going to be constant. Okay, this is important. When you throw a ball straight up and there is no horizontal motion, all of the potential energy becomes kinetic energy in the horizontal direction. But when you fire a projectile has a constant horizontal velocity, so that constant horizontal velocity means you're never going to lose all your kinetic energy. Now, here's an issue. Is energy a vector or a scalar? It's a scalar. Energy is not a vector because if it was a vector, you could not have a horizontal thing turn into a vertical thing. And you could not have a vertical thing turn into a horizontal thing. Or you could not have a diagonal thing turn into a horizontal thing. Energy is not a vector, energy is a scalar, which means energy is energy is energy is energy. It doesn't matter. For instance, the vertical potential energy here turned into horizontal kinetic energy there. So this had vertical potential energy turning into horizontal kinetic energy. Back to semi-vertical potential energy. So energy is a scalar, not a vector. Horizontal can turn into vertical and back again. Next, a pendulum. We actually have an entire unit on what we call harmonic motion. or motion that goes back and forth or up and down. We have a whole unit on simple harmonic motion. But just understand that, take a look at the graphs for, did it just stall? Oh, there it goes, okay. Take a look at the graphs for potential energy and kinetic energy. They do a lot of the same thing. You know, like most pendulums, they come to a stop. They come to a stop, then they go back again. They come to a stop. So where is the potential energy maximum?
At either stop
At either end. And where is the kinetic energy maximum?
in the middle.
In the middle. And where is the potential energy zero?
It's not.
It's not. A pendulum can't have zero potential energy, because if it did, that would mean it's like dragging along the ground. Unless we arbitrarily make the 0 point the bottom of the pendulum, which we can do, we can arbitrarily say the bottom of the pendulum is 0. But unless we do that, in this case, like the reference point's right there, the pendulum doesn't have zero potential energy, because it never actually reaches a 0 point. But the relationship still